Hello, oceanography students. At this point, you should have watched the first atmospheric circulation video as well as a video on Coriolis effect. And we're going to go on to talk more about how the air circulates in our atmosphere, and we'll also learn about prevailing wind patterns in this lecture. Okay, so we already learned about how it's hot at the equator because the sun is hitting the equator most directly. And so that air heats up and hot air rises. And then at the North Pole and the South Pole, because it's cold there, cold air is more dense and therefore it sinks, right? And so we end up with this kind of circulation pattern where the air at the equator rises up, it hits that barrier called the tropopause, and then it spreads out in both directions. And then eventually that air gets colder and colder and denser, and it sinks down. And air always moves from high pressure to low pressure. So what we end up with is a big circulation cell, or what we call a convection cell, okay? Heat rising and then cold air sinking, okay? Where air is rising, we call that a low pressure zone. The rising air essentially creates the low pressure zone. And whereas air is sinking, we call that a high pressure zone. And that air is basically creating that high pressure zone, okay? But we also learned that our Earth's rotates, and therefore the circulation of our atmosphere is not quite as simple as this. There's actually multiple places where air rises and multiple places where air falls. And so instead of just having these two big circulation cells, we have multiple circulation cells in between. All right, so that's what we're going to learn about today. We're going to learn how to draw those circulation patterns. Okay, so because our Earth spins, air gets deflected either to the right of its intended direction in the northern hemisphere, or if we're talking about the southern hemisphere, it gets deflected to the left of its intended direction. And at the equator, there's no Coriolis effect. All right, so here we can see our Earth rotating. And interestingly, when you would think the Earth is rotating, it's rotating from the west to the east, right? You could say something like that. But if you look at the Earth from the North Pole or the South Pole, it gets a little bit trickier to say which way Earth rotates, because if you're looking down on the Earth, and you can kind of look at this video to see this, if you're looking down on the Earth from the North Pole, looking down on the North Pole, the Earth actually circulates excuse me, the Earth actually circulates counterclockwise. But if you go down here and you look, the Earth actually appears to be circulating clockwise, all right? And so that essentially makes it so that the way that the air is deflected is different in the North Pole and the South Pole, and right at the middle, there's no effect by Coriolis. There's no Coriolis effect, all right? So I'm going to try and show this to you. If you want, it might be helpful for you to get out a piece of paper and kind of draw a big circle and act like you're looking down on the North Pole, and then get another piece of paper and draw a big circle and act like you're looking down on the South Pole, okay? So looking down on the North Pole, here is our Earth. All right, so right here, this would be the North Pole, right? This is the Arctic Ocean right here. This outer circle represents the equator. So we're essentially looking at Earth as if it's been like flattened, with the equator being the outer part, all right? So I'm going to try and draw on here for you. Where's my pointer? There we go. Okay. Now, bear with me because it's not very easy to draw on a keyboard, but when we look from down on the North Pole, our Earth looks like it's circulating counterclockwise, all right? So what I want you to do on your piece of paper is where the North Pole would be, just draw an N, and then I want you to put your pen right at the North Pole and draw a straight line as if it was going from the North Pole towards the equator. If I can draw a straight line here. Okay, now what I want you to do is I want you to try to draw that line again. Put your pen right back at the very North Pole, and I want you to try to draw that line again, that straight line going from the North Pole to the equator. But this time I want you to make your paper rotate like this, okay? And if you do that, then what your arrow should end up looking like is something like this, all right? That is showing you the actual path of the air that is moving. It can't move straight because underneath it, the earth is moving. Okay, so it's just like in that video that you watched where the kids were playing on that that merry-go-round and they were throwing the ball, and the ball, like, they tried to throw it to somebody, but it didn't go to them because that person was turning as the ball was going straight. So it kind of looked like the ball turned, but really the ball was going straight and then the merry-go-round was turning, right? That's the same thing that's happening on our Earth. Okay, you can do it also from the North Pole going to the equator as if you're going in this direction. And when you do it that way, let me go back to that. When you do it that way and you again rotate your paper just like this, what your arrow should end up like as you rotate your paper is like this. Okay, so when you look down at that, you're like, wait a second, now it's going to the left. It's not going to the left. It's actually still going to the right of the intended direction. So this is really important. If ever you're asked which way something is deflected, make sure that your original arrow is always pointing up, and then you'll always know which way is right or which way is left, okay? So for the northern hemisphere, it's always going to go to the right of the direction, all right? Southern hemisphere, we look down on our planet as if we're looking at the South Pole, okay? So here's Antarctica right here, and again, this outer circle out here represents the equator, all right? So in this case, when we see our Earth rotating from that direction, it looks like it's rotating clockwise, all right? So we're going to do that same activity. So you're going to get another piece of paper or right on the other side of the piece of paper, and you can just, where the center is, just put an S for South Pole. And again, we're going to draw an arrow straight going from the South Pole to the equator. And if you are to rotate your paper clockwise now, as you try to draw that arrow again, what you should end up with is an arrow that looks something like this. Okay, so you can see with a clockwise moving Earth, the air gets deflected to the left of its intended direction. Okay, you can do the same thing, pointing it downwards. And then again, rotate your paper so that again, it's going clockwise. And your arrow, if you try to draw it from here going down, your arrow should then look like this, all right? And then again, that looks like it's going to the right. But if you turn your paper over and point your arrow up, that arrow is, that reflected arrow is going to the left, all right? So the air is always going to get deflected to the right of its intended direction. Of its intended direction is an important thing to remember, okay? To the right of its intended direction in the northern hemisphere, and to the left of its intended direction in the southern hemisphere. So in order to see that, just always make sure that whatever way you draw your arrow, you turn your paper so that the arrow is pointing up, and then you can figure out which way the deflection is, okay? All right, so Coriolis effect causes something that's in motion on our planet, such as air or water, to be deflected to the right of its motion in the northern hemisphere and to the left of its motion in the southern hemisphere. And at the equator, Coriolis effect is going to be 0. All right? Now, this is going to be important to remember when we write in just a few minutes. We're going to actually draw the prevailing wind patterns, and those wind patterns are going to be based on both the air circulation patterns and the Coriolis effect. Okay, so you'll have to understand Coriolis effect in order to draw the prevailing wind patterns. And then in a future lecture, we're going to learn about ocean circulation and the major currents, and those currents are also going to be deflected by Coriolis effect. So it's important that you remember this and be able to deflect things, air or water, based on a direction that's given to you. All right, so what we actually end up with is circulation that looks something like this. All right, we still have air rising at the equator, and we still have air sinking at the poles, the North Pole and the South Pole, but then you also have air sinking at 30 degrees north and 30 degrees south, and air rising at 60 degrees north and 60 degrees south. Okay, so I am going to, 60 degrees south is down here. Okay, so I'm going to actually draw this for you because this map, although it does show you the Earth in the background and shows you the wind patterns and such, it's a little bit difficult to see the actual circulation patterns on the outside. All right. So I'm going to draw on this map of our Earth, all right? So this big circle represents our planet, and the major lines of latitude that are important for atmospheric circulation are 0 degrees, or the equator, 30 degrees north and 30 degrees south, 60 degrees north and 60 degrees south, and 90 degrees north and 90 degrees south, okay? All right, so it might be helpful if you draw this on a piece of paper and follow along and try and draw it yourself and make little notes about why you're drawing what you're drawing, okay? You will need to be able to do this on a test, and so I really want you to please don't try to memorize what we do today. I want you to understand it so that you can draw it with understanding it. Not just trying to memorize this arrow goes this way and this arrow goes that way, because you're going to probably mess up and it's not going to make sense and you won't be able to explain it. Okay. All right. So we're going to start at the equator. I think that that's probably the easiest place to start, right? You've got the sun that's beating down on the equator, right? That causes water to evaporate, and it also causes the air that is along land to get hot, all right? So if you add water vapor to the air, or you make the air hotter, the air is going to rise. And you probably see this if you boil water in a pan, you'll actually see the steam rising up. That's the same thing that happens at the equator on our planet. All right, so I'm going to draw, let's draw it on this side actually. So I'm going to draw an arrow going away from our planet. I don't know why that little thing happened there. All right, right here, we're going to say is the tropopause out here. All right, so again, the tropopause acts as a barrier at the very top of the troposphere, and the troposphere is where the majority of our weather comes from. So I'm going to draw this little dotted line to represent that tropopause. Okay, so the tropopause is there, and if air hits that tropopause, it's not going to go farther. Instead, the air is basically going to spread out from that point. Okay, so that should be good. All right, so once this air that is rising up hits the tropopause, it's going to spread out. Right? So up here, these arrows that I'm drawing right here, this is in the upper part of the troposphere. All right, so this is right here is going to be close to land. Up here is going to be up in the upper atmosphere. All right. Now, remember that from the last lecture, we learned that as you go up in the troposphere, the air temperature decreases. Okay, so that means that this air that is moving up here is getting colder and colder and colder. Now, what does that do to density of that air? You should be saying that it makes it more dense, okay? And things that are more dense are going to fall. So it just so happens that this falls just at about 30 degrees north, and this air right here falls at about 30 degrees south. All right? So what kind of pressure system, or pressure zone, I should say, has been created at the equator? Rising air means low pressure, okay? So we've got low pressure here. And what kind of pressure has been created at 30 degrees north and 30 degrees south? You should say high pressure. Anywhere where their air is sinking is high pressure. Okay, so I'm just going to write high on this line of latitude. Okay, so it's going to be high on this whole line of latitude, even though I'm only drawing it over here on the left. All right, and again, this one is also going to be high. Okay, so something to remember, another thing to remember to know this, is that air is always going to move from high pressure to low pressure. And this was discussed in the previous video, and I kind of related it to if I'm in a crowd and I feel like I'm squished, I want to move to an area where I'm not squished. And so that's sort of like moving from high pressure to low pressure. So as the air falls down, it's going to move away from that spot in both directions. Oops, drawing it funny here. Draw it like that. Okay, so we now have a complete circulation cell between 0 degrees and 30 degrees north. Okay, so we have a loop of air that's circulating here. And we have another loop of air that's circulating between 0 degrees and 30 degrees south. Okay, a complete circulation. Now I'm going to jump up here to the other place where it's really easy, and that's the North Pole, where we know that the air is really cold, and cold air is very dense, and therefore it sinks. So I'm going to draw an arrow that goes from the tropopause towards Earth. And I'm going to do the same thing here at 90 degrees south. So I'm going to draw an arrow that goes from the tropopause towards Earth. Okay? Now, just like we drew over here at 30 degrees north and 30 degrees south, and I didn't draw the other arrow going that way. There we go. The air is going to spread out as it sinks. Okay, so it's going to go this way from 90 degrees south, and it's going to go this way from 90 degrees north. All right, so now you should notice that coming up on 60 degrees north and 60 degrees south, you've got arrows that are going to be meeting. So what happens when those arrows meet is that they are pushed up. So again, we've got another location where air rises. All right, now just as the air that rose here at the equator spread out in the upper troposphere, the air at 60 degrees is also going to spread out. Spreading this way and spreading this way. Okay, so now we've got circulation between 60 degrees north and 90 degrees north that is a continuous loop of air. We've got circulation between 60 degrees north and 30 degrees north that is also a continuous loop of air. We've got a continuous loop of air between 30 degrees north and 0 degrees. All right, we've got one between 0 degrees and 30 degrees. Okay, when you draw your arrows, there should be a complete circle. They should all be going in the same direction when you draw that circle. All right, and then here, 30 degrees south and 60 degrees south, you've got another circulation cell. And then here, between 90 degrees south and 60 degrees south, you've got another circulation cell. All right, now we're going to move on and talk about the climate that gets created in those areas. okay? So let's start at the equator. We have a low pressure zone at the equator, which means that we have moist, warm air that's rising up. It gets up into the colder air. Now, if you take water vapor and you cool it down, what's going to happen to it? You should say it will condense or turn from a gas back into a liquid, okay? So what we end up with is that water vapor rises up, it turns back into a liquid, and then it falls right back down as rain. So at the equator, we have warm, rainy conditions. Okay? At 30 degrees north and 30 degrees south, the air that is sinking has already lost its moisture. It's dry, very dry air. Therefore, it's not going to have this climate. It's going to be dry rather than rainy. All right? 30 degrees north, dry. I don't know why it keeps doing that. There we go. 30 degrees south, dry. All right? Anywhere where air rises, it's going to be rainy, and where air sinks, it's going to be dry. All right? So right here we've got rising air, which creates low pressure. We didn't write our pressure zones up here. And just like the equator is low pressure and it's rainy, 60 degrees north, low pressure, rainy. All right? And that's because you've got air that is rising up, getting colder, and releasing it back down as rain. 60 degrees south, also low pressure. Air is rising. That creates low pressure. And where there's low pressure, there's rain. Now, at 60 degrees north and south, it's a little bit more complicated than that, and you're going to learn about that in the next lecture video, where when you have cold air coming in contact with hot air, what happens is that this hot air right here, as it's moving along the earth, it's basically evaporating water. So you've got water vapor in it by the time that it gets here. And when it meets with cold air, that cold air is more dense, so it basically pushes down below the warmer moist air, and that warm moist air gets pushed up. And when it gets pushed up, it gets colder, and you end up with rain that comes down. And then finally, the last one we didn't mark is the North Pole. North Pole is going to be a high pressure zone, and high pressure zone, just like 30 degrees north and 30 degrees south, is dry. All right, and 90 degrees south, same thing, high pressure because air is falling, and again, it's going to be dry. Okay, I'm going to change the color that I'm using here. Let's see, let's change it to blue. And now we're going to draw the prevailing wind patterns. So this is the circulation up in the upper atmosphere, right? This isn't really the prevailing wind. However, we're going to use the arrows that are closest to Earth. So this one, and this one, and this one, this one, this one, and finally this one, to figure out how our winds move, all right? So between 30 degrees north and 0 degrees north, the air is moving from 30 degrees down to 0 degrees. Now, if the Earth was not moving, then our prevailing wind pattern would just be from 30 degrees north to 0 degrees north, or 0 degrees, just going south, okay? But remember that Coriolis deflects it to the right of its intended direction. So if you take this image that you're drawing right now and you flip it upside down so that the arrow is pointing up, to deflect it to the right, you should draw an arrow that goes like this. Okay? And we can do the same thing between 30 degrees south and 0 degrees south. We've got an arrow that's pointing from 30 to the equator. Okay, so if the Earth was not moving, this would be how the wind went. But now we're in the southern hemisphere and we do experience Coriolis effect between 0 and 30 degrees, not at 0, but between 0 and 30. So it gets deflected to the left of its direction. So this is what our prevailing wind looks like. All right, and I don't know why it keeps on drawing those weird lines. Now, to name the winds, winds are always named from where they come from. Now, the winds that are on either side of the equator are called the trade winds, and this is basically because it was the path that was taken by trade ships. So these are called trade winds, and the one in the northern part between 0 and 30 degrees north is called the northeast trade winds, and that's because it's coming from the northeast. Okay, so we've got the northeast trade winds. I feel like I'm in kindergarten right now. I think my kindergartner's writing looks better than this. Okay, trade winds. There we go. All right, these ones are the southeast trade winds. I'm not going to write out trade winds for you. You know they are trade winds. You should write that on your paper yourself because it's probably easier for you to write with your pen than what I'm doing right now. So southeast trade winds. Now we can move up between 60 degrees and 30 degrees. And again, we're looking at the arrow that is between 30 and 60, and it's closest to Earth. All right, so if our Earth was not rotating, then this is the way that the wind would go. But our Earth is rotating, and therefore it gets deflected to the right. Now, Coriolis effect increases as you move away from the equator, so the effect is actually stronger, and our winds end up going more like this. All right. So there's a pretty strong movement of the wind from the west to the east. Remember that winds are always named for where they come from, not where they're going. These guys are coming from the west, so we call them the westerlies. Westerlies, there we go, okay? Let's go down here between 30 degrees south and 60 degrees south. And again, we're looking at the arrow that is closest, that we've drawn, that is closest to the planet. And if our Earth was not rotating, this would be the direction that it goes, but because it is rotating, we have to deflect it to the left of its direction. So this would be a good time for you to flip your paper over so that your arrow is pointing up, and you can then draw your winds between 30 degrees south and 60 degrees south. And notice that these ones are also coming from the west. So these ones are also called the westerlies. I'm not going to write it out, but you should write it out on your paper. Westerlies between 30 degrees south and 60 degrees south. All right. Now we need to move up between 60 degrees north and 90 degrees north. And again, we're looking at the arrow that's closest. So if our Earth was not rotating, this would be the direction of the wind, but our Earth is rotating, and now we're all the way up farthest from the equator, which means Coriolis effect is the strongest. Okay, here we're going to deflect it to the right of its direction. So again, flip your paper over so that your arrow is pointing up, and then you could deflect it to the right. The right would be this way. All right, so I wish that weird thing's not happening. These winds are coming from the east, so they are called the easterlies. All right. And the last one that we haven't done yet is between 60 degrees south and 90 degrees south. Again, we're looking at this arrow. This arrow is pointing from 90 degrees to 60 degrees, which means that if our Earth wasn't rotating, the wind would be going this way. Because the Earth is rotating, the wind gets deflected to the left of its direction, which is in this direction, like this, okay? And these ones are also called the easterlies. All right, you should be able to draw everything that we just did on this map. You will have to do it on your test, and you also need to be able to explain why you drew the arrows the way that you did, all right? You also need to know which areas are low pressure, which areas are high pressure, which areas are rainy, which areas are dry. So make sure that you practice this. And again, I want to reiterate, I do not want you to memorize this. I want you to understand it, okay? You are much more likely to be able to do it correctly if you understand it than if you try to memorize it. So this is a much prettier map of the circulation patterns. So again, here you've got air rising, spreading out, and then sinking at 30 degrees north latitude, creating this circulation cell here. It rises, it spreads out, sinks at 30 degrees south. Then you have high pressure that gets created here, low pressure that gets created over here. Air is always going to move from high to low. So again, you've got a complete circulation cell here. And you can continue on just like that. The sinking air is always going to spread out on Earth, and then it's going to rise back up at the next major latitude. And then it's also gotten the wind patterns shown for you. The only thing I don't like about this map is that these winds should actually be more from the west to the east than they actually are drawn on here. So that's the only thing that I don't like about this specific image, but it does show you like kind of the general way, and it also tells you right here the names of them. So we've got the easterlies, the westerlies, northeast trade winds, southeast trade winds, westerlies, and easterlies. And they also have labeled the low pressure, high pressure, low pressure, high pressure, high pressure, low pressure, high pressure, okay? And we can also look at what we just drew if we're looking at it from the side, all right? So here's our atmosphere right here. Here's our planet. This is the equator. This is 30 degrees north, 60 degrees north, and then the North Pole here. So again, at the equator, we've got rising air. At 30 degrees north, we've got sinking air. At 60 degrees north, we've got rising air. And at the North Pole, we've got sinking air. This is also showing you the kind of climate there. So we've got rain here because again, we've got moist air that means water has turned into gas and it's rising up and getting colder and turning back into liquid and falling as rain. All right, this air now that is up here that circulates to 30 degrees north and also to 30 degrees south, it doesn't have any moisture left because it was all lost right here at the equator. That's where all of the moisture came out. So we've got very dry air that sinks down at 30 degrees north, and therefore the prevailing conditions at 30 degrees north all around our planet is going to be dry. However, of course, land features can also affect this and create more rainy conditions or more dry conditions as well. So this is just kind of a general global pattern. But if you look at specific regions, then we can see some other differences as well. Now, this is showing you the names of the cells that get created. So you've got a Hadley cell between the equator and 30 degrees north. The cell between 30 degrees north and 60 degrees north is called a Ferrel cell, and the 60 degree north to 90 degree north one is called a polar cell. I'm not going to have you guys memorize the names of those circulation cells. I just want you to know what the circulation pattern is. Okay. So it's these circulation patterns that create the predominant climate of latitudes. So it's rainy and warm at the equator, it's warm and dry at 30 degrees north or south, it's rainy and cool at 60 degrees north or south, and it is cold and dry at 90 degrees north or south. So what that means when it says dry, it means that it doesn't rain very often. It has a very low amount of precipitation throughout the year, at both 30 degrees and 90 degrees. Now, something that I want to bring up for us to understand is that climate is the weather of a region averaged over a very long period of time. All right, so weather would be day-to-day differences. Climate would be, what's going on over like 100 years. What is the normal weather like over a 100-year period? That's the average, okay? Or maybe even longer. I'm just throwing 100 years out there, but even longer periods of time. Whereas weather are the atmospheric conditions at a specific time and place, So we live at 38 degrees north latitude. So we are basically in a region where it should be dry. And we do experience generally dry conditions. We don't get a lot of rain throughout the year. But we could get rain, that would be the weather, right? It would be like, oh, it's rainy today. Well, that's the weather. But over the course of, over the course of a year, over the course of multiple years, we don't get a lot of precipitation here. And that's because of basically that we're in a generally high pressure area. Okay, so let's just review the air masses. And I should say that if you remember this stuff right here, you should be able to draw that circulation pattern and the wind patterns and high pressure, low pressure, that kind of thing. Okay. So air that is less dense rises and air that is more dense sinks. Okay, that should be the first thing that you memorize if you don't already know that. Conditions that make air less dense include heating it and adding water vapor to it. All right, so if you have water evaporate into the air, that's going to lower the density of it. And if you increase the temperature of the air, that's also going to lower the density of it, and that's going to cause it to rise either way. Conditions that make air more dense include cooling it or taking moisture out of it. All right, so if you've got air that is dry, that's going to make it more dense. And if you have air that's very cold, that's going to make it more dense as well. And that means that it will sink. An area where air rises is called a low pressure zone, and an area where air sinks is called a high pressure zone. Air will always move from high pressure to low pressure. All right, so think about where you've got air sinking on our planet. So at 30 degrees north or 30 degrees south or 90 degrees north or 90 degrees south, that creates a high pressure zone. So the air is always going to move away from that area after it's sunken. Okay, so the air along the surface of the planet between 90 degrees north and 60 degrees north is always going to be moving from 90 to 60. And then we can add Coriolis to that to look at our prevailing wind patterns. Okay. All right, if you have questions, please let me know. You can post them under the weekly discussion, or if you want a more immediate answer, you can email me or message me through Canvas. That's actually my preference, is that you message me through Canvas, because sometimes my emails get lost a little bit with all the other emails I get. And then also please answer these questions in the weekly discussion. What happens to the temperature as you go up in altitude in the troposphere? In which season is the southern hemisphere when the northern hemisphere is in summer? In which direction would a parcel of air be deflected if it is traveling from 30 degrees south to 60 degrees south? At which latitude does air generally rise? And in which direction, up or down, does air move to create a high pressure zone? All right, that's all that I have for you today. I will look forward to seeing you in lab this week. Thanks, bye.